Hi everyone. I don't belong here. So maybe I should talk about kind of where I'm from. I'm an array programmer. The array programming paradigm was invented by Ken Iverson in the late 1950s, actually, very early. Now, other programming language communities and mathematicians as well have been, for a long time, taking ideas from Ken Iverson and then forgetting where they came from. And I guess what I'm trying to get across here is that you're not done yet. So I'll talk about some of the things you've taken from Ken. One of them is this very quote here, notation as a tool of thought. It doesn't actually appear in the text of the paper Notation as a Tool of Thought, which is about APL, but it appears above the text. And it's pretty impressive, I think, that you can just, before you even start reading, learn something, learn that notation is a tool of thought, that the way you write changes the way you think. The other thing, well, the thing that I think you have not yet stolen is the outer product, which I'm going to be talking about. But I also think you should just generally learn more about the array mindset, and that will help you in terms of other kinds of programming. So now, as programmers, you learn, when you're learning programming, to break problems down, to think in steps, to do things one at a time, to traverse trees and so on, to work methodically. As APL programmers, we learn to think in big units, to work on, to put things together, to work on entire lists. So actually, you as a programmer have further to go to learn APL than a novice does. One of the first things that anybody who teaches APL will tell you about it is that it's actually harder to teach to programmers than to non-programmers. But I think that also learning both sides, learning when to go into detail, when to use a recursive style and work one element at a time, versus when to use an array style and work with many things all at once to try to hold the entire problem in your head. I think that knowing both sides is going to be very helpful in your programming and is a very rich, will really enrich your programming ability. All right, so I'll start with just the basics of APL. I have a GitHub repository here. There's a Dialog publishes. So by the way, the company I'm from is called Dialog. We make the most actively developed APL implementation, Dialog APL. And we publish this Docker container, Dialog. So this gives you some instructions to download and use it. It's not really too important to be able to run APL code for this because I'm going to show everything on the slides and I'm going to explain it all. But if you want to work with it yourself and kind of manipulate it, that's really good. I won't really have time to talk about why you're getting certain errors or things like that. I have a lot of material here. It's all... Oh. Yeah, so I have to keep moving every 10 minutes, apparently. Huh? Okay. Anybody know a reason why my browser would refuse to project? Yeah, so it's just whenever I switch the browser, it gives me a black screen.
Every time you switch the browser?
To the browser, yeah. xy. All right, I think it just doesn't like the ones with images. Okay, well, those aren't very important. As you can see glimmers of, we're going to start just by doing basic APL. So yeah, if anybody's gotten this Docker container running, that's great. If you haven't, that's okay as well. So function application. Oh yeah, I should talk more about the structure here. This talk is made up of a bunch of sections. They're fairly different from each other, especially at the end. And I'd really like to get the ones at the end, and I know I won't have time to do all of them, so I'm kind of trying to go as fast as possible. So if you have kind of questions about like the more details of APL, like how it handles this edge case or that, or how the parsing works or something like that, I'd really prefer not to spend a lot of time on those. I'm trying to cover like the broad strokes here. And I'll be doing a lot of very different topics. So there's no one like single goal here. I'm trying to approach array programming from a lot of different perspectives, and so maybe give you a good idea of what it's about. But basic APL. In APL, we follow, it's a sort of more regular mathematical notation, very influenced by mathematics. So every function is either a prefix function or an infix function. Here is an infix function. You may have seen it before. Here's a prefix or monadic function. Monads are just functions with one argument. What's the problem? Here's a more interesting dyadic function. This is the combination function from mathematics, which is written with parentheses and two numbers over top of each other. It's very related to the factorial, so we use the exclamation mark for it. This is the number of ways to choose 2 things out of 5. There are 5 ways to choose the first and 4 to choose the second, except then reordering them, you have to divide by 2. We can also name functions very easily. So here I've assigned the times symbol to the function times, and then I've applied it as an infix function, exactly the same as if I'd used the symbol. Now if we have multiple functions, how are those used? APL, just if you're evaluating, it goes right to left. You can also think of this in a more functional way as opposed to an imperative way, as saying every function applies to the value immediately to its left and to the entire expression to its right up to an enclosing parenthesis. We have parentheses, of course. So to evaluate this, first I'm going to multiply 2 by 2, getting 4. Then this function, you can see it has no argument to the left of it. It has a function to the left of it instead. So this is a monad. It could be a dyad. We have a minus as well as a negation function. But here it's negation, so we negate 4 and get minus 4. Here we have a left argument. So 3 divided by minus 4 is minus 0.75. And then we add and get our result. Now, the reason we can do this, and the reason why we can have this syntax that looks so much like mathematics, is because we distinguish functions and arguments to functions. So I don't know why I'm allowed to speak here, but APL is not a functional language at all. There are a lot of drawbacks. The last one is the thing that keeps it from being anything like a functional language. At the very syntactic level, there is no way to apply a function to a function. It does not work because if you have multiple functions written in a row and an argument to the right of them, they will each be executed monadically. And there's no way to call them on functions. We have some other issues arising from this. In APL, if you assign a value to a function, this is also kind of tied into our assignment syntax, which is much more complicated than it needs to be. If you assign a name to a function or an argument, you can't then change your mind about which one it is. And this is really rough for us as implementers. The grammar of APL is not context-free. You have no way of knowing how a list of names parses until you know what the names are. So with all these drawbacks, it must be a pretty great idea if we're using it, right? In fact, there are some pretty big advantages to having this distinction. It lets us see things in this mathematical way that's very compact and works very well with functions. And I think actually, partly due to this syntax, while functional languages are far better than APL at manipulating functions, APLers have much more respect for the functions themselves. And they're able to do more powerful things just using functions. So I think the functions that are available in APL are far better, like just the primitive functions, the ones that are written with symbols, are way better than any other language. And the capabilities that gives you are really quite impressive. So I'm going to start with arguments. What kinds of arguments do we have? We keep it very simple for the programmer, except when we don't. You have just numbers and characters. And conceptually, these are just floating point complex numbers. Like, say, JavaScript or Lua, we use only floats, only doubles. But actually, we also have complex numbers. And characters are just Unicode. Now, we actually store these, depending on what their values are, in potentially very different representations. So that's actually one of the major advantages of APL, is that under the hood, when you have an array that consists of, say, all integers that would fit in 1-byte signed integers, it will almost always store them that way, which is a lot faster. Now, there are some other things that we do that don't fit this model and make everything really confusing. And also, we have another very useful kind of argument. You may be surprised that the L in APL does not stand for list. Now, these are not linked lists, by the way. We have a construction called stranding. I showed you what happens when you put functions next to arguments. When you just put arguments next to each other, what you get is they're put together into a list. So here's a list which is just printed the exact same way you wrote it. Here's a more complicated list. Among my arguments for the list, I can, of course, use other lists. Now, the default output for APL is not really too good for this. It's good for showing you what's in there. It's very bad for showing you what the structure is, which we're very interested in this talk. So what I've done by default, if you're using the instructions on the GitHub repository, but what you'll need to do yourself if you want to see this cleanly on your own copy of dialog, other languages this is going to work differently, other APLs, is set box on. So then this gives you a really nice box display. And we have a list that contains one character, one list, and a list of characters. So strings in APL are just lists of characters. And you write them with quotes, but actually if you only write one character, so if you write 0 or more than 1, you get a list of characters. If you just write 1, it's an individual character. Now we get to something exciting about APL. The functions, these just basic arithmetic, works directly on lists without any trouble at all. So you have two lists and you want to multiply them together, and okay, it does it, going element by element. If you have even a nested list, and you want to test it for equality against a character, it does that as well. Now, as I said, we only have the only basic bottom level types are numbers and characters. We don't have a Boolean type, so we use zeros and ones. This may be frowned upon in the functional community. I don't know why I'm allowed to speak here. But it is also very powerful for a lot of things. So you get a lot of advantages from using like specialized Boolean-like types, but you also get a lot of advantages from just using numbers. Reminder, you will need to set box on if you want to see things boxed nicely. The other setting that I have in the GitHub repository is what's called the index origin. APL offers you a choice to have indices for your lists, start at 0 or start at 1. I don't. You need to have them start at 0. Now, I said you can't take functions as arguments, And this is true because when you pass them to other things, they're called operands. So functions are not first-class citizens in APL. They're second-class citizens where arguments are first-class citizens. But we also have operators, which are kind of third-class citizens. So they're higher-order functions. And what an operator does is applies to a function as its operand, one or two functions. And then this can be applied to one or two arguments as its arguments. Now here's where the terms monadic and dyadic get kind of confusing, because a function, functions aren't inherently monadic or dyadic. You apply them monadically or dyadically, as I showed. So minus, it can have a left argument, or it might not. Operators always syntactically are what's called monadic operators or dyadic operators, which is different because it's inherent in what operator it is. So here I've shown the commute operator, which is a monadic operator. It always takes one function on its left. There are also, you'll see on the next slide, dyadic operators, which take a function on the left and one on the right. Yeah. So on the other hand, once you've applied that, so the operator itself determines how many arguments it can take. But then once you apply that, you get a function, a derived function. And then that, like any other function, can be called monadically or dyadically. Sometimes it will give you a domain error if it doesn't want to be called monadically or dyadically. But as a matter of syntax, you can always do so. And what the commute operator does is, so you can apply it monadically or dyadically. Dyadically, I'll pronounce this swap. It flips the two arguments, so you get 5 minus 2 is 3. Monadically, it has one argument and it doubles that. 4 minus 4 is 0. More on this valence stuff. And also a historical note about some appropriation here. Ken Iverson invented the bracket syntax for floor and for ceiling. And so this was adopted by mathematics actually after, or maybe while mathematics adopted those paired brackets. What Iverson actually did was drop the closing bracket, thus making them regular functions like any other. So the monadic cases of this L-shaped bracket and upside-down L-shaped bracket, these are floor and ceiling. And the dyadic cases are the maximum and minimum functions. They have two arguments, and they take in this case, the minimum. The other thing that has been widely distributed from APL is reduction. So anytime you see a reduction anywhere, that was in APL from very early days, I think before 1960 actually, and was only ever introduced to like Lisp in the late 70s. So APL was way before anyone else on having reductions. But back to operators. You can see here the first one. That's an example of a monadic operator making a derived function which is applied monadically. It's a min reduction, so the least element of that list is 0. The second one, when you have a reduction but you pass in a left argument, I mean, this is kind of, just a notational choice to pair these two ideas together. What it does is takes that left argument and makes that a window length. So it moves in windows of 2 along the right argument and takes the minimum of each of those 2. And you get, min 2, 0 is 0, min 0, 3 is 0, and so on. After that, we have composition. Now, the only composition operator that we have in APL is kind of weird and really just awkward when you're programming. But what it does is essentially it does the same thing as would have happened if you had written just a space there. Now, it's different because it actually creates a derived function, which you can then use later, passing to more operators or something like that. But so here, the monadic usage I have, it's monadically, it is the same as mathematical composition. So that divided by sign on its own, that's the reciprocal. It kind of has a default left argument of 1. So it's going to take the reciprocal of 0.5, which is 2, and then negate that to get minus 2. then yeah, the dyadic case, you can imagine it without this little circle we call jot, without a jot in the middle, and it still takes the reciprocal of 0.5 because there's no argument to the left of reciprocal, and then it subtracts that from 3, giving you 1. Okay, and APL doesn't have any precedence among functions or, well, really within any of these classes. But it does overall end up with a small precedence table. So if you're going to evaluate an APL sentence, and yeah, especially don't worry about this operator line. This is way more complicated than anything I'll show. But if you're going to evaluate a sentence, the first thing you have to do is stranding. So remember, if arguments are right together, they form a list. This is going to be a big problem for us. You strand first. Then after that, you apply your operators to functions to produce derived functions. And this goes left to right, the opposite order of function application, which sounds very awkward, but it was a deliberate choice. And it actually seems to work better in practice. It's kind of weird. But yeah, it works left to right. And in order to do it, you have to actually either know for each operator how many operands it takes, or find someone who's willing to put little numbers underneath them. So to evaluate this, we'll first have go from left to right. The minus gets a reduce applied to it, and then a commute, and then it's jotted with minus 2. And I didn't say this, but operators can take either functions or normal arguments. That's fine. So this jot with a normal argument operand it's like partial application, sort of, except, well, it binds an argument to a function. We don't actually have, we have real two-argument functions. So it binds an argument to a function. So it produces something that can only be called monadically then, and is called with this bound argument on the side that it's bound on, and with the operand is a bound argument, and then the actual argument that you apply on the other side. And then this is composed with the reverse function. And then after that, you can apply your functions in the same way that I showed. All right, so there's the easy parts of APL. And this slide says questions, and it's going to flicker very awkwardly. Maybe my laptop is just really weak. Yeah?
Could you say again the difference between operators and functions?
Okay, so as a matter of syntax, functions are allowed to apply to these basic arguments, numbers, characters, and lists. Operators apply to, they kind of apply to functions and lists, but they never do anything in APL at that point. So they're always going to take operands and then take arguments. They're higher order functions, but it's a very specific kind of model. Anyone else? Yeah?
What's the difference between top bar and...
What and what?
The difference between top and bottom?
Oh, yes, that's important.
Top minus sign and middle minus sign.
So the middle minus sign is a function.
Bottom minus sign.
Yeah.
I see them both on that last slide.
Yeah. Oh, it's good that I put them together then. I wasn't even thinking about that. Let's go back so I'll have that visually. Yeah, the middle minus is a function, and that's negate or subtraction. The high minus is a part of a numeric constant. So this -2 is one token. And the reason why that's useful is that, like I've shown at the top, you can write that in a stranded list. So if I'd written that list with a minus, it wouldn't parse right. It would not be what I want.
I wish we had that in Haskell.
Oh, yeah, there's an example on this slide where I had to write like -1 plus, and I was so frustrated. Anyone else hoping this is pretty easy so we can get on to like real stuff? Right, moving on then. The outer product, it is an operator, but it's written real weird. And this is because it has this history of being, Ken Iverson thought of it as a special case of the inner product, which is a generalization of the matrix product. And that's just a really complicated way of looking at it. So I definitely won't introduce it that way. But it does have the result that the outer product has this weird syntax. The inner product was written with a dot. The outer product is actually 2 characters. And unlike most operators, which go to the right of their operand, monadic operators, the outer product goes to the left of its operand. So it's written jot dot f, where f is a function. Jot is the little circle, so jot dot f. So the subjects, well, yeah, so it's just like a multiplication table. And here's how you produce your multiplication table. This is our first kind of serious APL phrase, so I'll break it down for you. Going from right to left, we have iota 12. Now, the iota is actually another thing that's been adopted by a lot of languages, also introduced by APL, although the idea of calling this iota is not really that great of an idea. But the function itself, what it does is to produce all the indices for a list of that length. So a length 12 list has the indices from 0 to 11, and so it's going to produce a list from 0 to 11 for us. And then, because we usually don't care about what happens when we multiply things by 0, we're going to add 1 to that. And then what we're going to do, now this is a derived function produced by 2 operator applications. What we're going to do is, so the way this is parsed is it's jot.times, so it's a multiplication outer product, and then commute is applied to that. And it's called monadically, which means, based on commute, it's going to take its argument, and it's going to make it both the left and the right argument. So we have 1 to 12 on the left, 1 to 12 on the right, and we're doing an outer product times on it. So what the outer product does is to produce a result that's, it applies the function to each pair of elements from the 2 arguments. And the way it's written is that, now this is symmetrical, but the first argument corresponds to all the rows, and the second argument corresponds to the columns. So every function application is written in the row and column that corresponds to that pair. So you get this table of all the possible products of 2 elements. Yeah?
Was that on the previous slide, was that a period after the dot product jot?
Is
Jot period x?
Yeah, that's, so the circle is called jot, and the period is called dot, so I pronounce that jot dot very quickly.
And it's the dot that's the outer product?
It's both that's the outer product. It's really weird.
So it's effectively it's a function that has 2 characters in its name.
Yeah, you really don't want to write the parsing code for this.
Right.
You'll be expected to memorize this table, by the way. An example of something useful you can do with the outer product, and also with numeric booleans. So here we've got 2 different arguments to the outer product, a much simpler outer product. We have an equality outer product. So this is going to take, for every pair of a character from A, B, C, D, and every character for the string cabbage, it produces it compares them and produces a number. So we get this grid of where each of A, B, C, D is equal to these. So you can see the top row corresponds to A's, and there's 2 A's in cabbage, and so on. And then what we can do with this result, what we're trying to do here is find how many times each of the numbers A, B, C, and D appear in the word cabbage. So in another language, you might break this down and say, first, as a subproblem, I'm going to figure out how many times one letter appears in the word cabbage. In APL, we don't do this. We treat this as an entire computation. So first, we do all the equalities, And then we're going to do a plus reduce. Now, there are two forms of reduce as I've written. One goes along rows and one goes along columns. So I've done the one along rows, and it just sums each one up and gives us a number of characters. There are 2 A's, 2 B's, 1 C, no D's. So that's a pretty useful computation in a very small amount of space. And this is also because equality can be vectorized, because summation can be not vectorized, but you can use, well, we use bit booleans, so we use pop count, which is even faster than vectorized code for bit booleans, which is nice. So that this is also a very fast way to implement it. Another example, here's how they make Chinese menus. Well, they don't use APL yet. We're hoping to get into that market. You have a list of meats that you might want to include in your food. I would have included vegetarian, but it goes over the edge. And you have a list of styles, and it's going to show each combination in a grid. And it only takes a little bit of stuff that you don't understand to turn this into a nicely formatted menu with numbers. So here I've used another outer product where I add some last 2 digits to some first digits. Another cool example is Pascal's Triangle. Now, as a triangle, it's not really grid-shaped, but actually writing it as a grid is interesting, especially if you go into negative numbers, because you start to see the other side of Pascal's Triangle. But what I'm doing here is it's the same kind of structure as that multiplication table. I'm not adding 1 because I do care about 0 now. And I'm applying the combination function. So for example, the 7 at the top is the number of ways to choose 1 item out of 7. So that's kind of interesting. It's Pascal's Triangle is one way to lay out all the combination numbers. This is a way to do it in an array language. Interesting fact about Pascal's Triangle, if you take all the values mod 2, you get this cool fractal pattern that's known as Sierpinski's triangle. So yeah, not much APL. I hope the mod is self-explanatory. Except it's not insane like it is in C or Java. It handles negative numbers well. Okay, so some mathematical properties of the outer product. What happens when you exchange the arguments of the outer product? 2 things happen. First, every single application of your function is reversed. And second, because we always lay out the first argument vertically and the second horizontally, the axes are reversed. So if we want to undo this, or just say what's really happening, we can apply two things back to this to turn this reversed argument case back into a normal case. So first, I've shown the operator that reverses the arguments. So we apply that to the function, so it unreverses each function call. And then we have transpose, which just works like a mathematical matrix transpose. Yeah?
So for operands, if you're applying it monadically, the function appears on the left, whereas functions, when they're applied monadically,
Yeah, that's right.
appears on the right.
Yeah, so operators and functions are kind of all mirrored because the associativity is backwards as well as the placement of the operand argument. So yeah, here's our kind of first interesting mathematical property. The x jot.f y is the same as the transpose of y jot.f swap x. Now, what if f is commutative? What happens, well, by definition, if f is commutative, then f is the same as f swap. So what's going to happen is that it's only transposed when you swap the arguments, and it's not the swapping doesn't do anything. Yes?
So previously in some examples you used swap literally. Was this for ergonomics, or was this?
Like I said, the word swap, or?
No, just like Sierpinski's triangle and the
Oh, did I say, I should be saying self for jot dot, I should be saying jot dot choose self here if but yes. Oh, did I not explain that? No, yeah, we'll need this. This is APL's anonymous function syntax. So it's like a lambda, except that you don't get to choose what your arguments are called. If there's one argument, it's always called omega. The right argument is always called omega. And if there's a left argument, it's called alpha. So here, this function is I'm taking my left argument and applying the catenate function, which will join either a list and a, well, it'll join any two things. So if you've got two single things, it'll turn them into a list. If you've got a list and another thing, it'll join it to it. And if you've got two lists, it'll join them together. So I'm applying that and joining them with the space. Thank you for reminding me about that. Yeah, we were going to get a long way without knowing what defins were. Okay, back to commutativity. Yeah, so what we can look at with commutative functions, well, we can ask, so if the two arguments to an outer product are the same, then, of course, swapping them does nothing. So swapping them does nothing, but it also, from the last slide, it commutes the function and transposes the result. So if we look at this an outer product, and we compare that outer product with its transpose, then those are the same if and only if the function was commutative. Because it should be the case that transposing and also commuting the function is the same as swapping the arguments, which is to say doing nothing. So if you just transpose and that does nothing, that means that also commuting the function did nothing. So here at the top, I've shown, now I'm writing another defin here, and inside this defin is a stranded expression. That's just for display here. So I'm stranding the original argument with the transposed argument. And I'm going to apply this defin first to jot dot less than self iota 4. And this is a nice way to generate these diagonal, like upper triangular, lower triangular, and so on matrices, actually. Quite useful if you're doing matrix algebra. But here I can see that if I transpose, the result of this outer product is not symmetric. If I transpose it, it's different. Which means that less than is not commutative. I hope I've taught you something.
Hang on a second. So how do we know that the thing in curly braces is not the left operand, not the left argument of the outer product?
Because the outer product, so whenever you have operators applied to functions, I mean, you have to do all the operators stuff first, and that requires knowing what each operator, how many arguments it takes. And in the case of outer product, that it's this crazy syntactic thing. Once you do that, if you get a function such as, so here, this jot dot less than self is a function. Now you know you have the pattern function, 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 argument. Just by applying that pattern. None of these functions have arguments on their left. They all have functions or nothing on their left. So they're all applied monadically. Yeah, with jot dot equality on the other hand, nice way to produce the identity matrix. And also the identity matrix is symmetric, as we can see, either by looking at them manually with our own eyes or by asking APL using the match function written with these 3 lines. We ask, does W match its transpose? And APL says yes, and we can conclude from that. I'm not going to actually prove anything in this talk, but we can conclude from that 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 equality is a commutative function. Yes?
Is the triple equals like a matrix equality?
It's whole thing equality. So the reason why we need a triple equals and a double equals is that double normal equals, even as, well, no, not, match would actually work the same way in the place of equals here. But equals in general, like if you give it to lists, then it will map over them. So if you want to know whether they're the same list, that's not very helpful. And also if they have different lengths, it won't map over them, it'll give you a length error. So we had this match which tells you, are these arguments as entire arguments the same? And here it returns 1, they are. You can also take multiple outer products. So as an example, this would be the last step in computing the divisors of 60. If I have 60, I can get all its divisors by taking the prime factorization. And then every divisor has at most that many prime factors. So I can choose, for example, 60 has a power of 2 to the 2 is a divisor of 60. So every divisor has either 0, 1, or 2 multiples of 2. So I've written 1, 2, 4 there. And same for 3, it's either a multiple of 1 or a multiple of 3. Same for 5. So we do this 3-way outer product here. Now it's just 2 normal functions being applied in sequence, but it gives us a 3-dimensional result. Now APL doesn't have like a whizzy 3-dimensional display, and you wouldn't want it if it did. So to display a 3-dimensional result, we write slices. So as before, the last axis goes along the rows. You have 1 here, 5 here. The second to last axis goes along the columns. And the third axis gets a sort of super, more spacing vertically, I guess. So there are 3 cells of this result, 3 2-dimensional cells, and each of them is shown with a space between them. Now, what? Oh yeah. Keep 15 times. We would really like to fix that, but it's actually it's not that we can't. We can very easily change the number in our code, but in order to be backwards compatible with old stored stuff, well, and forwards compatible with stored arrays, it's really hard to change. So yeah, the maximum rank in APL is 15. The last thing I'm going to show about outer product, or describe at least, is that if you have an outer product and the function that you're outer producting is associative, then this outer product is itself associative. So here my function is catenate. This is associative on lists, because if I join if I join 3 things together, it doesn't matter in what order I do them. They all end up in the same order in the result. And here, the same thing happens. So if I want to say, going from left to right, that I've written a book and it has 2 sections, and each section is in each section is 3 chapters, and in each chapter is 5 paragraphs. That's exactly the same as saying, I've written a book which is composed of chapters. There are 5 paragraphs to a chapter, and 3 chapters in each section, and there are 2 sections going the other way. It's exactly the same thing. So questions about the outer product? Yes?
In the previous example, why does ABCD...
Yeah, I really should have made it actually a list of lists, but I should have made it a list of lists, but here it's a list of characters. And yeah, all lists are really the same kind of thing. The 2 of them in this example happen to contain other lists, and one of them happens to be a list of characters. That's okay. And join is a tolerant function. It accepts many kinds of arguments. So.
So how come we don't get, like, how come we don't do that for every character in any of the other lists? Like, why don't we get, like, 1 period 1?
It's a 2-rank list, or a list of lists.
Yeah, well, it's because it's, I mean, outer product works, it treats both its arguments as lists. It doesn't care what's below. Specifically, it doesn't map down lower than that level. So it always goes kind of one level into its arguments.
So, whatever name doesn't care what they are given?
No, it does care because,
But
I mean, it,
can concatenate
yeah, yeah.
If you concatenate a list to a list and a list to a single item.
Yeah, exactly. So it's actually, if you're doing like theoretical work, catenate is pretty awkward, but it's very useful for programming. Anything else? Moving on. Now, this slide says it in black, but it says array programming. Now we're going to get to really the, well, start getting into the meat of this talk. Yeah, when I said the L in APL doesn't stand for list, actually, it doesn't, but the A in APL, more surprisingly, doesn't stand for array. There's a common kind of backronym, array programming language. It's actually named after a book by Iverson called A Programming Language, so it's a programming language. It's the only one named after this fact. We really pride ourselves on the way, like this is a true thing that we're proud of the way we name things in APL. We didn't do a good job on the language. Okay, questions you might have about array programming. I'm not going to answer what's programming for you. And also, I'm not really going to answer what's an array. But I can tell you that an outer product, like I've been showing, is an array. And actually, the way I want to describe arrays here is to say that an array is something that's shaped like an outer product. So it's got this rectangular shape, and you can put anything you want into the spaces, but it has that shape that comes from doing this grid-like operation on multiple things. So here I've shown an example of an outer product, just pretty much like we saw in the previous slide. So these things are, well, yeah, this is a very interesting outer product because each space kind of tells you how to get to it. So this top one here is cell 0, row 0, column 0. And over here we've got like cell 0, row 2, column 2. And actually APL, using the index generator, will generate exactly these indices for you. And these are the indices it uses to index into an array, an operation which will not appear at all in this talk. Yes?
If you do I, that's not I2 and then separately 3, 4. It's like I on the 2, 3, 4 list.
Yes, yeah, so this is stranding here again. And it's pronounced iota, by the way. But yeah, so we're calling iota on the list 2, 3, 4. Maybe I should have put another space in there. Yep, just strand before function application, always, and even before operator application.
And could you put the iota outside parentheses?
No, because then it would first compare the list 2, 3, 4 to this big outer product. It's always going right to left, and then it would take, it would get 0, and then you get iota 0, which is a surprisingly contentious topic. Okay, yeah, facts about this array. It's a three-dimensional thing. We say it has rank 3, and its shape is produced by looking at the shapes of each list in the outer product. So, if you have an outer product of lists, the shape of that outer product, the shape of that array, is just the lengths of those lists put together into a list. And the rank is the number of lists or the length of that shape. And if you're doing an outer product with array arguments, like this first one is the second outer product you do, the leftmost, has one rank 2 array on its right. Here's another example with 2 rank 2 arrays. If you do an outer product, it just catenates the shapes together. And yeah, when I wrote this talk, I was kind of worried about introducing a technical term like monoid to describe something so simple. I now know that it's only for historical reasons that this is called LambdaConf and not monoidconf. This is just a very simple description. A monoid is kind of like a group without the inverse requirement. It's exactly a group without the inverse requirement. The kind of archetypal example of a monoid is lists under catenation. And shapes work just like that. So if you take the outer product of two arrays, their shapes are catenated. And that's a monoid operation. But the interesting thing here maybe is that actually also arrays of lists, lists because of the weird way that catenate works, form a monoid under outer product catenate. And so monoids have this associativity requirement to be called a monoid. And in the case of shape concatenation, catenate is associative on these shapes. And in the case of jot.catenate, that's associative because the outer product preserves associativity. So this shape is actually a monoid homomorphism, or I'll call it a transformation, just for simpler language. It's a transformation between the monoid of arrays of lists under jot.catenate to the much simpler monoid of shapes, which are lists of natural numbers. And what it means by a homomorphism is that it takes, it preserves this monoid operation. So if you take the shape, it distributes over jot.catenate and turns it into catenate in a way. So it changes arrays to shapes, and it changes each instance of jot.catenate to a catenate. Gosh, it's hard to fit things in slides. There is another way to store multidimensional data, and that's the way that many programming languages use, which is to nest lists in this way. So don't really worry about the details of split, but here at the top left, I've shown a rank 3 array. This is how we write, this is called a flat array because it's not nested. All its elements are single characters or single numbers. But you could also, the same data could be stored in a rank 2 array, which contains lists, or even a list of lists of lists. Now, these are pretty different models of storing multidimensional data. And I'll get into that in a little bit. The first thing that I'd like to do before that is kind of an aside that I'll bring up later. Originally in APL, we kind of thought of arrays as they have these dimensions, and all the dimensions, they have an order to them, but they're basically on equal footing. So for example, we have these two reductions, slash and slash bar, that one works on rows and one works on columns. And well, you can even specify an axis using brackets to say I want one of the ones in the middle. But actually, one of the very surprising discoveries in APL, and one of the things one of the reasons we now call it modern APL was the development in the 80s of this idea called leading axis theory, which is that the leading axis is kind of privileged in a special way, and that actually, even though arrays aren't nested lists, we want to sometimes treat them like that. It's useful to treat an array as a list of major cells whose length is the first axis, whose length is the first element of the shape. That is, the list goes along the first axis. So for example, I produce an array here using the GCD, and this has 3 cells, each of length 4. So I can ask APL, how many major cells does it have? Yes?
What's the counterclockwise routine?
Oh, yes. That's actually just the identity function. So by default, when you do an assignment, it's not printed. One way to make it print is to write an identity function there. So this is called write-tac. it always returns its right argument. There's another one called left tack, which when it has a left argument, returns the left argument. And otherwise, as a monad, it's the same as right tack. Yeah.
Places you've had a box character, is that a mistake or is that actually an operator? Like on the last
Box character?
I thought it was a broken glyph, but it looks like it's a real thing.
Oh, yeah. This is, yeah, I should have said what that is. The box is used, yeah, this is really awkward. This was way before Unicode, guys. So the box is pronounced quad, and it forms a part of identifier. So quad A here is a single token, and that is the uppercase alphabet. So quad is typically used for like system functions. So you'll have like quad in read, reads you a file, and gets as just a list of characters.
So is it safe to say that anything that appears after quad is like built into the language essentially?
Yeah. Yeah, so this idea of leading access theory, we have found, and I will explain why this is, that it's a really good idea to, even though arrays are not nested lists for reasons that I'll explain, sometimes treat them as nested lists, sort of. So for example, unique. This is not actually necessarily present in all dialects of APL. We added it to dialog APL pretty recently in maybe 2013, 2014-ish. No, after that. It was while I was there, so like 2016 or 17. Yeah, so we can, unique now, it works on major cells. And this was, by this time, the obvious choice for us to say, well, unique just takes all the cells which aren't duplicates, so it throws away the duplicates. It preserves the order, but removes everything that was already present earlier. And it was the obvious choice by this time to work on major cells. Now, arrays are not nested lists. Go back here. I've shown here how, given any array, you can get a nested list that has the same data. And many languages kind of identify these. They say, well, a multidimensional array is a nested list. This is not true, because with the nested list model, you can actually write more things. I could write, each of these leaves has length 5, but I could make one length 6 and one length 2, and there are lists of 3 lists here. I could make them different lengths, and you get what are called ragged arrays. So the list of list model is actually can express more things. So arrays are really limited. All they do is they prevent you from doing things by saying you have to have this rigid multidimensional structure. So why would you do something? Why would you limit yourself? And I would suggest that most of you do that. You take a perfectly good program and then you apply constraints to it in the form of types. And arrays do the same thing. In dialog APL, you have an array, and it's like a list of cells, and you add this requirement that every cell has the same shape. So this is weird pseudo-Haskell, because writing arrays in Haskell is absolutely nuts. The idea is that an array is kind of like a tuple. So this SH is a shape, and an array is this length L list of arrays of that shape of its cells. And actually, some array languages go even further than that, like the Sharp dialect of APL, and J, which is Iverson's invention, a successor to APL. Some of them go further and say also at the bottom level they must have the same type. Either they're all numbers, they're all characters, or they're all this special new type called boxed, which kind of is the escape hatch for this construct. And this is a real difference. This is not just the difference between static and dynamic typing is a real difference, and similarly, the difference between nested lists and arrays is a real difference. The way I like to think of this is to say, and actually I think yes?
What defines major cell other than being the first element of its array?
It's not the first element. So the major cells are, so a cell of an array is like a subarray. It's like one of the rows or one of the two-dimensional subcells. Major cells are the largest dimensional proper subarrays. So an array is always a list of major cells.
Is that like
Yes.
saying that that's your top level data structure, or like the top level container of all your data structure?
Sort of.
It's in terms of an array, or it's like viewing an array as a list of slices.
Yeah. Well, and it's pretty easy to see in this this pseudo-typed model. An array is a tuple of its major cells, sort of concept-wise. Yeah. Nothing. Yes, I think that the difference between static typing and dynamic typing is really that with static typing, even before you do anything, even before you do a computation, you know something about the result. It's type. And similarly, with arrays, now there's not this idea of executing or any sort of time dimension, but even if you have no major cells, even if the first axis of an array has length 0, you still know what the shape of those cells is. And this actually shows itself in APL programming. So this array model, all it is a restriction on nested lists. And yet, what that gives us not only is some advantages that are very much like static typing, but also that because it's more restrictive, you know more about it. And on these advantages, actually, a very similar advantage to static typing allows you to make programs that compile to be faster because the compiled code knows what type it's getting, and it can be written exactly to get that type in the proper way. Like, it doesn't have to check the type of its arguments at runtime. And arrays are the same when you know that the type of all the elements is the same. So even though we don't use this model where all the leaves are the same type, we still store arrays. We try and figure out what the type of the arrays is, and we store them as either numeric, character, or boxed. And this allows us to do the exact same thing, which is to write computations that already know what type they're taking, and thus can go faster. And also, this is even more of an advantage with arrays. So arrays, if you have a large array, you can process it even faster than you would do processing in a compiled language without arrays, because there are these vector instructions. So this array model, where things are contiguous in space, is sort of like a super static typing in performance terms. But yeah, on programming differences, if we look at empty arrays, we'll find that they actually behave differently in an array language versus a language that pretends to have arrays. So, and a preliminary example maybe is transpose. If you have, in Haskell, you have a list of 3 empty lists. This is like a shaped 3-0 array. If you transpose it, all you get is an empty list. If you transpose it again, I think you just get the empty list back. You've lost information. In APL, the transpose is always a self-inverse, which is a really nice property. But yeah, so here's a 3-dimensional empty array. This 0 with a tilde through it, that's pronounced Zilda. That is the list of no numbers. So yeah, it's not well grounded theoretically like our shape system is, but empty lists also kind of store type information, which is called a prototype in dialog. So the list of no numbers is actually different from the list of no characters. Yeah.
Does the Zilda appear basically where any normal character or number appears?
Yeah, it's.
And how does it strand?
It does. It's a list, so it's the same as if you had written a list in parentheses. That strands with other stuff. Zilda, it doesn't have parentheses around it, but it's an empty list. So if you write Zilda 1, that's a nested array its first element is the empty list. Its second element is just a plain 1. So yeah, we have here an empty array. Well, it's not that different from a normal array. What? Yeah?
This is like just another really odd question, but like what happens, so it sounds like you can have arrays that are heterogeneous, right? You can have different things in each slot or in each cell.
In dialog, yes.
So what happens when you outer product two heterogeneous lists?
So all outer product cares about is that its arguments have the structure of a list or an array. So it applies the function to the elements of that array. Those elements can be anything at all. They can be different from each other. So I won't show any of those, but it does.
So like most functions don't work on both numbers and character lists, right?
Yeah. At least by the counting definition of most, I think. Yeah, I mean, so APL is a dynamic language. You can do all sorts of, you can put whatever type thing anywhere. It's dynamically typed, but it does get statically typed advantages through arrays. So yeah, what can we do with this empty list? Let's sum along the columns. So yeah, this array, we can tell it's different from that first empty array, actually, from the APL output. It's not super clear here. But the first one, it's printed with one empty line, and the second one is printed with no empty lines. And you can actually work this out. What's happening with the first list is that there are two cells. Each cell has no rows. So it prints two cells with no rows, which are separated by an empty line, because they're two-dimensional cells. And each of them has no lines because it has no rows. Now, after we take the sum, oh yeah, and reduction. This bit, when reduction was exported to the other programming languages, this has been completely lost, but actually the reason, not entirely the reason, but a large part of the reason why Iverson called it reduction is because it always reduces the rank by 1. So this slash form of reduction always takes the first axis away. It reduces along the columns, and it turns each column into a single element, thus dropping the first element of the axis. So that's, if you need a single reason, that's why reduction is called reduction. I mean, it's also kind of, it just feels like, it makes the array smaller, except in this case. So yeah, the first time, maybe it's not too complicated. We're summing two cells, and each of them is empty, so we get an empty result. The second one is kind of weird. So the input has shape 0, 4, and we're asking to sum along each of the 4 columns, each of which has length 0. So again, this drops the first axis. That axis has length 0, and it leaves us with one axis of length 4. So the result has to be a list of length 4. Most languages with reduce would complain about this. APL has a fair amount of code to try and figure out what the identity element for the reduced function is. And the result has to be an identity element because because of the way reduction interacts with catenation, not like necessarily the catenation function, but just jamming arrays together. If you put an empty list on the front of a list, that can't change the reduction, and yet the result of this reduction has to be the same as the reduction of the empty list applied with the function to the reduction of the other list. So the result has to be the identity element. APL tries to figure out an identity element. I mean, for plus, this is just a lookup on the functions. If it can't find one, it gives you a domain error. But otherwise, it will actually tell you the identity element of this function, which is pretty cool. So APL has this algebraic knowledge that you can get out.
Can you give it one if you can't figure it out?
No. Yeah, so APL knows about the identity element and inverses of some functions. There is a proposal to tell it about the inverses of functions. There's nothing yet to say what the identity element is, because that's not super commonly used, except for pretty simple functions like. So yeah, if you really need it to handle the identity element, you can just append something before reducing. Yeah. There's no reduce with initial element. This really bothers me, and I think there should be, but there's not. Okay, yeah, so I said earlier that arrays form a monoid under jot.catenate, and I said jot.catenate is associative. To be a monoid, there also must be an identity element. Yeah, and I also said that shapes form a monoid, and I didn't say what their identity element is. So that's pretty easy. The identity element of catenation is simply the empty list. So I've shown here, if you catenate the empty list to some stuff, then it doesn't change it. That's an identity element. For jot.catenate, it is harder conceptually. We might just very naively try Zilda. And this doesn't work. If you think about the way outer product is working on shapes, this is an outer product where the left argument is an empty list, that is an array of shape 1, and the right argument is an array of shape 3. So the shape of this result is going to be 0, 3, which is not the same as the shape of the right argument. In order to be the identity element, the identity element would have to have shape an empty list, because this monoid homomorphism, just by the abstract properties of homomorphisms, you can prove this, has to transform the identity element into the identity element. So the shape homomorphism would have to transform this identity element to the empty list. But it does not transform Zilda to the empty list. Now I'm going to distract you for a moment. Another interesting question about arrays, which ties into monoids, is how many elements are in an array? This is fairly easy to answer. This is the rectangular area formula, the cubic volume formula, and so on. It's the product of the dimensions. What's more interesting about this is that the product of the dimensions is a monoid homomorphism from arrays to the monoid of natural numbers under addition. And it's actually formed by composing two monoid homomorphisms. First, from arrays, the shape from arrays to lists of natural numbers. And second, the times reduce from these lists to, did I say under addition? I meant under multiplication. To the natural numbers under multiplication. So as an example of this, here, first I've written out the product of 2, 3, 4, 5, because I know you didn't memorize that multiplication table when I asked. Next, I'm showing what's called the bound. What is the product of the shape of an outer product? This is all these elements multiplied together. Next, what is the product? I'm just applying the shape homomorphism, basically. So that shape homomorphism, it turns each array into its shape, and it turns jot.catenate into catenate. And then next, I have another homomorphism, which is turning these shapes into bounds, and it turns catenation into multiplication. And then I find the bound of that array. Now, actually, this idea of the bound is going to help me to determine the identity for an outer product. And I really wish I could tell you that Dialog APL can find this identity. And in fact, version 18 can, but it's out next year. So it's been in there for a long time. 18's been a long time in development. So it could even before I did this talk, but not the version you're getting. But we know that the identity element of the addition outer product has to have a bound of 1. And so that means it's an array with just one element. Now the choice, there's kind of an obvious choice, which is the identity for addition. So let's make it, let's just write a one thing, which is 0. And we can plug this into APL, and it works. What's happening here is that even scalars I've said that lists are arrays with rank 1. Even scalars are arrays, and they have rank 0. They have empty shape. So yeah, and we can consider how all this works with monoids. The product of that empty shape, the bound, that's the product of an empty list, which has to be the identity for multiplication, 1. And this all follows from the properties of monoids. Now let's attack the identity for jot.catenate. This also needs to be a scalar. It needs to be a rank 0 array, empty shape. But it needs to contain something. It needs to contain an empty list, the identity for catenate. The way we do this is with a dialog function that's called enclose. So we take Zilda, the empty list, and we enclose it to produce a scalar. And you can see from this application that actually you can insert it in the middle of an outer product. This is associative, so you can think of this either way. But it doesn't do anything. It is the identity. So just a summary of this section, and then we'll get to our break finally. This is a table of monoids and one not monoid. The tally is actually a semigroup, but don't memorize that. It does have an operation. It is associative. It does not have an identity, so it's not actually a monoid. Going through this list, I have, so you've got an array. Arrays, as I've said, form a monoid under this operation, jot.catenate. If you have an array and you want to get the whole array, you can use the identity function. And the identity for the array monoid is this enclosed Zilda. Here's an example of an array. Shape, you get it using the shape function, monoid under catenate, identity example, so on. Tally is interesting. So we take the tally is just the first element of the shape for arrays with rank higher than 1. For scalars, we actually, in dialog APL, make the choice that the tally of a scalar is 1. So we say it's kind of it has a major cell and it's itself. And this is really kind of wrong and not on a good theoretical backing. What we really should say is that it doesn't have major cells. It doesn't have another axis. So we say that the tally is 1, but actually what we should really do is make the tally return a maybe number and say that the tally of a high-dimensional array is that first element entry of its shape, and otherwise it's nothing. And then it would form a monoid, because you could combine tallies correctly. So I've shown here the operation is the left identity. With maybes, you would say it's the left identity, unless the thing on the left is nothing, in which case it's the thing on the right. And that's another monoid. It's, it's a projection sort of the monoid of lists. And then rank. So yeah, the message for this section, this is what array programming is. Everything is an array, even the things that don't look like arrays. So I've been using the term list. We don't use that in APL because we don't have lists. We have arrays, right? So we have terms for arrays of various ranks: scalar, vector, matrix. This is the actual terminology in APL. I'm probably going to keep using the word list, and even in APL, I kind of say list a lot because there is no such thing as a list in APL. So you may as well call a rank 1 array a list. There's nothing stopping you. Yep, that's array programming for you. Any questions about that part? Yep.
So what does the split operator do if there's no distinction between lists and arrays? It's not that there's no distinction, it's that we only have arrays. Like, I just say lists for rank 1 arrays. That's not official APL terminology. Split always turns the rows of an array into rank 1 arrays, vectors.
So the shape of something that's been split is just one dimension?
No, that's how it should work. It actually drops the last axis. That the shape is with one axis dropped, and then the shape of each item is that last axis.
And how do you get an array of length 1, vector of length 1?
You apply typically, you apply the monadic form of comma, which is called ravel. What ravel does to an array is always turns it into a vector simply by dropping all the shape information. It turns it writes all the elements in order, left to right, top to bottom, turns it into a list. So on a scalar, that turns it into a length 1 list. So yeah, typically, it's awkward, but like if you want a list of characters, you can write comma, quote A, quote, something like that. Anything else? We will then take our overdue break. The slide for this is really nice, guys.
Why is the projection system doing that?
I think my computer is failing in some way. Yeah, I don't really know, but it doesn't like it. Maybe it's the browser, but hard to say. Good question. Does anybody know how long the break is supposed to be? I haven't been in any of the other workshops.
We've got 30 minutes left, so 5-year slot, so.
Yeah, I know. Let's just take 5 then. Wait. Does that mean I get like another hour, basically? Yes. Oh, this is the greatest. Oh, we're gonna do so much cool stuff. We're gonna get to the very end and find that I didn't write the slides at the end because I knew I wasn't gonna do them.
Maybe you could show us some of the simple.
I can talk forever. Huh? We'll get another hour easily. Like if people are tired, we can collectively decide to. Huh? Let's extend it. Well, do people like want to take a? It seems like good. Yeah. So 10. Come back at 5:05.
Will you get to like Conway's by the end of the presentation or no? Conway's getting like.
I won't be doing that.
Okay.
I did that once in APL.
It's not very hard.
Yeah, I haven't shown to me before, but it's never explained.
Actually, the cool kind of mathematical thing I'm going to do is the Cantor set, which is easier, so I can go into it in more detail. But we'll do some really cool stuff along those lines.
Yeah, sorry, it's just like it's very dense if you've never seen it before.
Oh, yeah.
Single symbol, like,
I can't
you
imagine going to that video like.
show any of the
Yeah.
symbols. Like, it's helped a lot with just basic rules.
Yeah.
Like, they follow.
So what's in the John School's Gain of Life? You might actually be able to follow the whole thing after this. Anything? Yeah, I think we go over pretty much all the primitives in there, so you'll have a pretty good shot at it.
Is APL fairly unusable for standard programming without?
Nope. Oh, without.
That you're working on, if you will?
Well, Dialog is an APL like language. It's in 80s style. We have entangled the IDE with the language.
My question is more like interacting with web services, doing normal stuff.
Oh yeah, we can do that.
I can write a web server in it.
Yeah. There is a web server called My Server, which is
Descriptive.
yeah, it's MI server. Don't know why it was named that. This is the part of APL that I don't work on, so my information is not that good. But yeah, we do some, like we have companies that are selling
serious products to clients with GUIs and everything based on APL as standalone applications. So it's usable for this stuff. Yep, we have very good bindings to .NET, and we have bridges to Python, R, Java, probably other stuff.
APL from those languages, or?
And vice versa.
Is there much use of APL in data science?
Not really.
It seems to
There's-
be well suited to it.
Yeah, and unfortunately they've got stuck on MATLAB, which is just degenerate APL. Like, it's really, if you know APL and you use MATLAB, you're like, these guys messed it up.
I was going to ask you what the relationship was, because I know quite a few people that use
Yeah.
MATLAB, and when I knew APL first, and when I looked at MATLAB, I thought, hey, that's kind of like APL without funny characters.
Yeah, well, kind of. And, like, you know how nice this everything is an array idea is? Like, because everything actually is an array? They decided instead everything is a matrix. And you know, not everything's a matrix.
Yes. How do people generally keyboard APL these days?
Yeah, that's the other part.
Depends on the operating system. But yeah, it's well supported. There's a way to do it on every operating system.
So you mean you just have a special layout and then a composed key to get
Yeah.
the APL characters to the alphabet?
Yep.
So you just
And-
have to memorize the keyboard layout.
Well, you can just also use a table for a little while.
Yeah, so there's also, in the IDEs, we have a bar at the top, the language bar, which has all the symbols. You can click on them, you can hover over them for information about them.
Like there's an APL font, so you can do this in your regular editor.
Yeah, well, APL's Unicode, so.
Would you mean that only on screen keyboard? Yeah.
Yeah, and there's also, what we also have is a backtick keyboard. So you type in backtick and another character. What's nice about that is if you type in backtick once, you'll get a completion menu, which you can actually scroll through as well. So that'll kind of teach you how to type things with backtick.
Oh yeah, that's definitely much more good.
Yep. So yeah, the characters are an impediment, but there aren't a whole lot of them. You can learn them, and there are ways to do APL without learning them.
Right.
When you define names or new functions, do you ever assign them the Unicode characters, or there's always kind of like the ASCII characters?
Names, I believe, have to be ASCII. We might support like accident characters. We definitely don't support general Unicode characters. No, you can't.
But really, what are the semantics of surrounding things?
It's happy. Those are its semantics.
I wonder if you get actually more
Yeah, well, I actually, I'm frustrated that J, so my first programming language was not APL, but J.
because the first programming language you ever
Yeah. First thing, other than graphing calculators. I had a high school teacher who, actually now he's working on the J implementation. And this is kind of the first time that implementation's moved forward in at least 5 years, more than that. But yeah, he taught me J. And I've been frustrated in the past because J doesn't allow Unicode identifiers. They could, but they've made the decision that it's too hard to, you know, distinguish between the Unicode characters you'd want and those that you wouldn't want, and identifiers. But what I wanted to use them for was that I had a tool to where instead of, you know, writing out LaTeX, I would write J, which would then sort of evaluate, but you know, under the covers it was my own system, and it would evaluate the J symbolically and produce LaTeX. And that way I could use like all the operators in J. I could use reduction, I could use, what we'll see later, power, apply a function many times. And yeah, I wanted to use Unicode symbols so I could write like sums and integrals. And I did, I just had a text replacement for it. And also there's, for a little while, I used a J extension that I'd hoped that was gonna catch on. That was like, you know, J's open source, so somebody extended it with Unicode characters.
Do you use anything else besides J or APL?
Well, my day job is writing dialog APL in C.
C?
Yep.
That's kind of hard. Whoa.
Actually, I find it's what I'm doing, like, yeah, C has its issues, like any language. But I find what I'm doing is not actually trying to solve problems, for which I would be really frustrated with C, because APL is great at solving problems. What I'm trying to do is describe computations, because I do high-performance stuff. So it's really a different kind of programming. And C is a very good language for describing computations on a CPU. So
It has a very clean mapping from source to the actual assembly.
Is that mostly for convenience, or why did you choose that route?
well, why did I choose C? Yeah, I didn't. In 1981, Dialog, the company, chose C. In 1981, Dialog chose C for its implementation language because, well, C was a good choice at the time. Also, we're really constrained in the languages that we even could use because we have a lot of clients on IBM Power, running on AIX, IBM's operating system. So we pretty much have to use IBM's compiler for that. Yeah.
Great, but we might get self-hosted APL implementation pretty soon.
Yes.
As in an APL, written in APL?
Yeah, so my APL is written in APL, but
Yeah, it is. It's a self-hosting subset of APL.
So there isn't like a technical hurdle of just getting to the work. That's what
yeah, it's just one.
we just chose C early, but
Probably from
Yeah.
very, very, very good reasons. Yeah, probably. It's still probably.
Yeah, and I've written my own language. I chose C actually for that as well. I would probably choose Rust today, but I'm not. For high performance stuff, I think C is probably still the best choice.
And actually, you guys aren't using portable C. You also have a lot written in assembly, don't you?
We have very little written in assembly now. A project I did 2 years ago was to replace all our arithmetic framework with C++ template metaprogramming to get vectorized arithmetic that didn't rely on assembly. So we use vector intrinsics. Not too much, but a fair amount. And yeah. Yeah, and so we choose except for power, for various reasons, APL is compiled for a generic architecture, and so we only ship one binary for a given OS and bit size, and we choose the vector instruction support at runtime.
Has anyone done an APL for more highly parallel machines with bigger vector instructions?
Bigger. We looked at. Do you mean like bigger, like AVX 512, or bigger?
Do you have a machine in mind? Right.
Ooh.
have one at home or something.
No, that's a pretty popular one.
Yeah. Crays are real in the supercomputing world.
So,
I've never heard of it.
what's the Craig's a custom CPU, right? Or does it have something I don't know. Been around a long time. Well, so
Yeah, I thought they'd switched to x86 a while ago, actually.
Craig's vector machine back then. That was we can support GPUs now, so like NVIDIA, ATI, AMD, those machines. Wow.
Well, we is Aaron.
Yeah, sorry.
Dialog will not run on a GPU.
So what's your
PhD student.
They have a license to my compiler, so if you want to buy the GPU compiler for APL, you talk to Dialog.
Yeah.
But it'll run on OpenCL and CUDA, those kind of architectures. So if there's a C compiler to an OpenCL engine on the Cray, there's a good chance that it may work. But I think there might be some stuff to play with there.
But APL would be a much nicer way to program this type stuff.
Oh, yes.
Oh, yes, yes, yes. So if you have an architecture that you want to support, it's fairly easy for you to try to target other systems. So if there's if you've got access to I don't have access to a crate, so I don't have to worry about that. But if you have access to that, that could be done. We can target that.
Kind of funny practical question, but what do you usually do when you want to answer questions that you don't know? A lot of other programming languages, it's pretty easy to just go search the internet and find something or at least talk to you. So does that trip up at all? Do you have to just rely on the network of people that you know? Or
It's getting better. It used to be
Yeah.
to use that and post it on Complang APL. You can still do that.
Actually, the Stack Overflow forum is going to be the place to go.
Yeah, the Stack Overflow is pretty good. Adam's pretty active there, right?
Yeah.
Yeah. So
And there are a lot of people, not even from Dialog, who are, well, and it's not a Dialog-specific forum.
so if I search like, how do I file APL, I should find something somewhere?
yeah. Also, Dialog has tremendous technical documentation in like 3 different formats that you pull off of.
Yeah, you just don't really see it on Google.
And then Dialog live streams a bunch of tutorial stuff and has videos of all of many of the past meetings. You'll see all of that. And then, but like, yeah, searching through Google sometimes is the most effective way to do it.
Yeah, and it often gets you old versions, so.
Yeah.
Um,
Is there a present somewhere? There is a APL subreddit.
It-
It's not there yet.
yeah.
Yeah, I would go to that for help. If you want to do some trolling or anything, there.
Well, even then, you won't get much action.
Yeah, the APL currently is still the most efficient way to use the technical resources when you've got questions that you can answer. Probably there's a contact one of the APLers, or do a Scrabble report or something like that, or chat rooms, things like that, because it's still kind of a very human endeavor. And the language has become a lot more modern, and the tutorials haven't necessarily caught up with modern practice. We are working on that.
I see a bunch.
The remote onboarding experience is something that we're actively working to improve on. So if you can keep a learning journal of your experiences and send that to us, that's very, very helpful for us to improve our tutorials. Like including do you have a thought on that? I might.
What?
It probably depends
Depend-
on how much you have to unlearn.
Yeah.
At least get a little
You really have to approach it openly.
And they actually do have a website that the competition is saying you should interview if you've never done this before. You can just pick it up.
Yeah.
So I think it really depends on what they're going to making the problem.
The hardest thing is going to be how quickly you can turn on the programming thing.
And it does, it is possible to write Fortran in any language. You can come to APL and learn a little bit of stuff and start programming and maybe learn more. Like, there are some very advanced techniques you can use in APL. And you can learn those as you go.
Maybe you should write an APL for the first principles. So I'm playing with that. The problem is, what are the first principles of APL? That becomes an interesting question. I've been exploring that for like the past 3 years. So,
There's no universal answer.
well,
That is the first thing is exercise.
yep. So, I don't know. I think if you give yourself a month of good study, there's no reason you shouldn't be capable of doing stuff. But you just have to keep. The problem is most people read about APL, they don't do APL. The big investment
Yeah.
is if you just keep writing APL, you learn really quickly.
Are there any tools like for the syntax
That's the
Or is that-
tutorial, right? The dialogue tutorial.
Yeah, well, there are a lot of different introductions. Actually, the student competition website has a very nice list of materials. So, yeah, what's it called? APL competition.
Dialogue programming competition.com.
Yeah. Dialogue, APL competition.com.
Okay.
And I'm not really into the allowing what's the thing which is out more, languages.
What's the question? Did you say A plus
Oh.
J with more modern?
Yeah, I mean, that's fair to say. J
J is
is more modern than old school APL. Dialog has been introducing concepts from J, but it's got, we'll see a whole lot in this section. Backwards compatibility is preventing it from really incorporating all the J ideas. However, dialog, like in the broad strokes, I personally think J is a better language than dialog APL substantially. However, in like the details, not just the implementation, but also like the details of execution, things like error messages, things like, even I think our array ordering, the way we sort arrays is better than J's. So dialog, it turns out to be a nicer language to use, and it's a whole lot faster than J. So you choose it for practical reasons.
So wait, you just said you think that is better?
In the broad strokes, I think the ideas, the underlying ideas of J are more developed, and it's been able to, in its design, because it's 30 years newer, avoid some of the problems that came from early APL. Like a good example is this outer product syntax. That's crazy. J doesn't use that. J uses a slash.
That's pretty terrible. I can see how hard.
Dialog is pretty nice for debugging. Actually, APLs in general are very nice for debugging because they come from this model of always working in the REPL and interactively, like the editor is part of the IDE and everything. So when you get an error message, our error messages aren't like incredible, but they're reasonably informative. They'll tell you where in the statement it had the problem. And there's a broad type of error, domain error, length error, rank error, and also usually, we're still adding it, but usually you'll get a message describing what happened and possibly, like for a value error, if you don't have a name defined, it'll tell you what the name is, things like that. And then after that, you are actually, at that point, you are suspended on the stack, and you can then look at the whole stack trace. You can see, you can move up and down the stack, execute expressions and everything. You can change the function that's executing, go back, redo it, continue execution. So very nice debugging.
You can sort of lie along the patch while you
Yeah. So a night.
And you can suspend that debugging session, send it over the network, and work on it on a computer.
Whee. Don't do that though. It's our testing for these kinds of things is not very good, so things may break. Actually, Morton, our CXO and CTO now that our previous CTO just left, he had a very nice phrase that he said he debugs code into existence. He starts with an empty function, writes a line, tries it, fails with an error, so he's debugging. He changes the line until it works, goes on to the next line. So through the debugger, he's writing the code. No, dialog's an interpreter, so it couldn't be. It's written in C. and C++, but really only for templates. Should I start back up? Oh yeah, that's right. They do the networking themselves. Come on, just starting right now. Okay, yeah, so our next section is, I talked about this leading axis theory being part of kind of the modern view of APL. The rank operator is really the core of this modern APL vision. The way rank works, dyadic operator, 2 operands. The left one has to be a function, the right one has to be an array. And yeah, in the first section I said argument all the time. We don't use this word argument, we just say array. So this is an array. And that's the thing that's different from functions. You got arrays, functions, and operators. And yeah, what it does is to say sort of this function only applies to rank 2 arrays. So if you give it then a rank 3 array, it's going to apply to the rank 2 cells of that array. To give us an example, they're duplicated, so now there's 4 of them. But I'll show you. This is, like many things in APL, we have these paired symbols. Here, both of these are called reverse. I think they're both just called reverse, actually. I can't remember the names for anything ever because I work on the interpreter side, and actually like everything in APL has one official name and then like a billion random other names, and those are typically the ones that are used in the code in the interpreter, so all my terminology is really bad. So we've got one reverse which works on the last axis, and then one which works on the first axis. So you see I've defined this array at the top, and I can reverse its rows, or I can reverse its, not really columns, but kind of super columns, the first axis things. Yeah, well, it does also reverse its major cells, but actually the way that it was thought of was in this old school APL style, where you're thinking of this as like sort of a bundle of length 2 arrays. Those are its like one-dimensional, like that's viewing it along one dimension, and you reverse each of those, which is equivalent to reversing cells. So yeah, if it's hard to visualize here because those length 2 lists are split up. On a 2-dimensional array, it's very easy to think rows versus columns. But here it's sort of super columns instead of columns. So here I apply rank 2 to each reverse. And so what this does is it, instead of applying these functions to the entire array, it applies them twice, once on each of these major cells. So reversing the rows does exactly the same thing, because the rows of the major cells are the rows of the whole array. Reversing on the first axis is now different. It reverses each column within the cells. So see, here's without rank, with rank. So the model of rank, it's sort of based on the rank you give. It's selecting a trailing subset of the axes. And it's saying, I'd like to apply my function on that trailing subset on those cells. And now what's happening is that these reverses are choosing one axis from their argument. So you see that when you choose a trailing subset, that means the endpoint is always the same, and the beginning point changes. So this reverse along the first axis changes, and in fact what we see is that you can implement reverse along the last axis just using this reverse with the horizontal bar, rank 1. And in case anybody hasn't seen it yet, these are kind of showing maybe flipping around an axis. So this is with the vertical bar, you're picturing flipping the array along the vertical axis. Horizontal one is flipping along the horizontal axis. So this is actually, like in J, for example, J has rank, and it only has one reverse. It uses this reverse, and if you want to reverse the rows, you write reverse rank 1. So this is making our language simpler by using rank to allow more functionality from a smaller number of primitives. Yeah. So here are some more examples. These are things that work along the first axis, even though, like, they were thought of originally as, like, the axes were seen on equal footing. So these things just kind of happened to work on the first axis. So here's a reduction on the left. On the right, this is called drop. So it just drops the first 2 elements here. Yeah, so reduction, I've shown, these red lines show you how it was thought of. And actually for reduction, this is not just conceptual. This is a real thing because it's not going to apply the function between cells. For plus, this would be the same. But for something like if you had an array of lists, this reduction is going to apply along the columns. So it's going to apply, like if you catenate those together. It catenates the lists along each column, and it doesn't do anything to the cells as a whole. Yeah, so here we can see rank 2, that works on the whole thing. Rank 1, that works on the rows, and it has the effect of turning this column-wise operation into a row-wise operation. So we got kind of lucky with drop here, because it was designed in old school APL, but it happens to work on the first axis, and there's no corresponding last axis function. So we got really lucky with drop there. We were unlucky with split, which works on the last axis, and there's no corresponding first axis thing. But actually we do have, no, that's not really true, because we have actually a 0th axis function, which I showed you. It's inclose. So split is actually the same as inclose rank 1, right? It's turning each row into a single array, or a scalar. Yeah, and that does the same thing as split.
Why have you got the identity functions in there, the tags?
Oh, yeah. Yeah, this is, I said stranding was going to be a problem for us. Take out the identity function. 1 strands with A. So, yeah. Operators with array operands are real problematic. And in the very, very early days of APL, there were none of these. The first was power applying a function many times, which we'll see later. And rank is another one, and they're really annoying. You have to either use right tech there, or I guess you could use left tech, but that's just perverted. Yeah, or parentheses. You can actually, cool thing, you can put parentheses around that whole + rank 1, or you can put parentheses around only the rank 1, and it binds the 1 to rank and turns that into a monadic operator. Yeah, that was rank with 1 argument. Does that all make sense? Can understand what it does.
Rank is a pretty critical concept, so it's
Yeah.
it's worthwhile if you don't really understand what's happening in the past.
Yes. And now I have time to answer. It's great. Yeah, so rank with 2 arguments. Yeah, well, what I'm going to use to show this is the membership function. This is another, like, in another language, you'd be able to say, you'd have a collection and you'd say, is a particular element a member of a collection. APL is an array language, so it works on a whole array at a time. For example, this left argument here, rank, I ask, is it a member of an array? And it gives me a Boolean for each character in rank. So I can do this membership all at once. But yeah, so it's asking for each character in rank. Is that character in the whole of the right argument array?
So R is in the
An array, A is an
A.
array, N is not.
Okay, because that's
Yep.
when I thought it was operating on the whole as opposed to being just here. But now I understand.
Okay, yeah. However, if we want to, so say we want to take rank and ask whether each of these characters is in several different strings. This primitive mix is the opposite of split. It's going to, so I've written a nested list using stranding there. And mix is going to turn that into a 3x5 table for me. And membership, this is seen as a mistake now, but it treats the right argument as an array as a whole, as a collection of elements with no structure to it at all. And it asks, is each character in that? Now, using leading axis theory, we really like to treat it as a list of its cells. Are these questions?
Yeah, the thing that is like kind of the numbers, I can imagine basically dependencies or duplication if it is a matrix or multi-dimensional arrays on multiple levels. So, but I'm wondering what would be coding for various parts.
No, dialog does not do any sort of sparse encoding. We are looking at a pretty interesting addition to the language that would allow the programmer to define their own sparse arrays, which still use the normal primitives in a way that the programmer has implemented. So the programmer says, like, basically overrides primitives, and then you could do sparse arrays that way. But no, we store all arrays completely flat, like, as, you know, the obvious representation on hardware, except that we use a small type when we can. Okay, yeah, so membership, well, for the particular question I've asked, membership doesn't work like we want it. So how would we ask, is rank a member of each of these arrays? We can call it rank 1. And so now it says membership has to work with rank 1 arguments. So the left argument is rank 1, and it will actually reuse it each time. And the right argument is rank 2, so it'll loop over that. So now you get 3 results, 1 for each row of that right argument. So rank, the R and the A are in array. Only the A is in shape, and the in is found in bound. Some other examples. APL is actually really great for text formatting. But first we have catenating with rank 1. This, so in the rightmost application here, it has a right argument, which is a vector already, so it reuses that and loops over the left argument. And I'm going to get into, like, I'll explain this more formally later. I'm just showing examples now. Then the second time, the left argument, it actually has rank 0, but that's less than or equal to 1, so it's fine. It won't, like, increase the rank or anything, but it will just reuse that. And so then you get, you've taken your array, which is 4-5 shape quad A. This is a shape 4-5 array whose elements are the alphabet. And it puts that a quote on the left and a quote comma on the right. Then, yeah, second, we have a more complicated function format. This thing just gives you the string representation of an array. So this is joining the string representation of the left argument to with a colon space to the right argument. And if I apply this with iota 4 and an array, and I call it, now I'm using 2 numbers, and one of them corresponds to the left argument, and the other corresponds to the right argument. I'm saying it needs to take rank 0 arrays on the left and rank 1 arrays on the right. And now, because both arrays are larger than that, it's going to loop over both of them. And then I get this list. So, yeah, to see how this works, let's look at a simpler model, which I said earlier that APL arithmetic works on arrays and didn't really explain it. The way that this works is I'd like to suggest that these are all pretty obvious answers. So if you take 2 to the power of iota 6, the only thing you can do is take 2 to the power of each element of iota 6. Star is the exponent. Similarly, iota 6 squared, you have to square each element. The 2 has to be reused, because there's no other right argument that you could have. Like, that's the only thing that even makes sense. Like, you can't move a left argument over to the right. That'd be crazy. And the final case, if they have the same shape, it'll loop over both. And the shapes have to match in that case.
And I assume you can do outer product that way as well? You give dot star.
Well, not really this way. Outer product is its own looping thing. So we have, I won't show you any loops in APL, and yet, we have already seen this scalar extension is a mapping construct, sort of, and rank is a different mapping construct, and outer product is a third mapping construct. So outer product is completely explicit. Scalar extension is totally implicit. Rank is sort of, it's like implicit, but you're giving this rank to control it. Yeah, speaking of rank and outer product, actually they're very closely related. What you can do with rank is, so yeah, we want to, outer product is kind of, it's extending both arguments, right? Because it reuses them both, sort of. It reuses each element on the left for each element on the right, and it reuses each element on the right for each element on the left. So we want to do 2 scalar extensions, actually. And this is almost like a nested application of rank, which of course you can do. So yeah, scalar functions work as if they have rank 0, right? Because that's why they're called scalar functions. A scalar is a rank 0 array. So scalar functions only apply to scalars. And the rules for these are unfortunately only very similar, but I won't explain why. Very similar to the rules for applying a function with rank 0. Now, if we want to turn this into an outer product, we need to do kind of 2 maps. One that extends so the outermost one is going to extend the right argument, reuse it each time. So loop over that left argument, but not the right. And the inner one is going to loop over the right argument, but not the left. And so what we do is we write only the outer one with rank. So we say it's 0 on the left. You need to loop over the left argument because it's a vector. And 1 on the right, which allows us to reuse the right argument. And then the minus kind of contributes a rank 0 to that. And this results in a minus outer product. And we can actually, so we've written 0, 1 here, which extends the left argument. If we extend the right argument instead, we get a transposed outer product because the choice of which time to extend was in the opposite direction. All right, so now here's finally the kind of the full picture of rank. So rank, what it does, it's specifying this shape or the cell rank to work on. But beyond this rank, we might have some leading shape. So here's a dyadic invocation of rank that's looping over both arguments. So beyond the rank that you specified, 3, 2, they both have leading shape. And that means it's going to have to loop over both of them. And it's going to require that these leading shapes match. Now, if one of them has no leading shape, then it just loops over the other one. It replicates that one with no leading shape, as though it's a scalar. Like it's thinking of that shape as a scalar, maybe, in analogy with scalar functions. So to force it to do this, to loop over the right argument, so two convenient deficiencies in APL. We have the deficiency that an APL has no infinity, and also that APL has no arrays of rank higher than 15. So we write f rank 99 too. So that means the left argument is always an appropriate rank to be reused, and the right argument's always mapped over. Same in the other direction. And I probably still don't even have time to go into this in detail, but I'll show what's going on here. So going back here, I've shown that you can do an outer product with rank, sort of. It's actually different because outer product always, it kind of nests its result. Rank flattens its result, basically. So you're looping over cells, and the results are cells. And that shape is directly, like those cells are not enclosed. The shape is directly appended to the result shape. You can extend this outer product. Actually, if you want to do an outer product, but not, rather than looping over the arrays, like looping over each element of the arrays, you want to loop over each row of the arrays instead. You can change this and use, so this 0, 1 is the same as 0, 99, right? Because this right argument is rank 1, which is less than or equal to both 1 and 99. So you can write function rank 1, rank 199, and that does kind of an outer product on rows, actually. So you can look at it and at least see it's very short. Two different applications of rank to compute the maximum distance among 3D points. So what it's doing is subtracting points and finding the length. And in one version, I've represented A as row vectors. So it's doing this kind of row-wise outer product in them. You see with rank 99, 1, rank 199, and doing this function that I won't really explain, and then it ravels it and takes the maximum of that. And you can get the maximum length that way. Or you could represent A as column vectors, and then the distances, you can get distances by doing a subtraction. Then you can work only on one dimension at a time. So you do a subtraction outer product, rank 1, meaning on each dimension of A. So A is column vectors. A has 3 rows, x, y, and z. And you take all the differences of x, all the differences of y, and all the differences of z. That gives you a rank 3 array. And then this length function, because I'm using a first axis model, works in both cases, which is really cool. So that was a really hard section. But questions about this, and we actually get to some functional programming after this one. Are we just lost? Which is okay. This is.
I started to make more sense when I just started with simpler problems. I mean, like I can follow some of it, but it's hard to like think it will do something there. It's like too far along this for me.
Yeah.
I'm just starting earlier, like with the membership function, or whatever you call it. I'm just reading
Yeah.
some thoughts.
Yeah. I think these next 3 sections are the ones that I really wanted to do. So it's great that I have time for them. And rank was definitely the hardest section. So don't feel bad about not getting that immediately. I'm trying to give you a concept of how array programmers think and the idea of working on arrays all at once and how something like rank enables us to do that. So if you don't get exactly the details of rank, especially dyadic rank, that's fine. And you'll learn them at some point in your APL journey. So typed functions, typed functional programming. You can write the obvious outer product in Haskell. It takes 2 lists and gives you a nested list back. You can write this using maps, right? So you're mapping over your first argument. The outermost map goes over the first argument. That's just an arbitrary decision. That's putting the first axis corresponding to the first argument. So we're mapping over that. And for each element of this, we're going to bind it to our function and map this over the right argument. So it's 2 maps. And you can see here, you get a little multiplication table there. Here's a more complicated example. If you've got interest rates of 3, 5, and 7%, want to compute what your total, the total multiplier over 1, 2, 3, 4 years, you can do an outer product with exponent. And we could very easily do that with APL as well. So does that function make sense there? It's mapping over one side and then the other side.
Had you thought about defining it with list comprehension? That's the way probably a Haskell program would do it.
Oh.
Double maps.
No, yeah, I don't.
Do you know what I mean?
Yeah, I didn't even remember at the time that Haskell had list comprehensions. I think in functions and operators sometimes, so.
Yeah, don't worry.
Yeah, I get that. Map actually makes this view a little easier. So maybe this clarifies a little bit what I'm saying with rank and outer product. The idea of this is that we're going to decompose outer product into saying map over the left argument, or map over the right argument. Yeah, then is not really the right word to apply, but take your function, turn it into something that maps over the right argument, turn it into something that maps over the left argument. So we define this map only over the right argument by saying, so we've got our function, and we want to treat the left argument as a single thing and reuse it, and the right argument as a list. So then we're going to map this lambda that says y goes to f of xy, of course, over y's. Now just simplifying, using some kind of getting towards point-free programming, we can turn this lambda, of course, is the same as a partial application, fx. And same in the full expression, this y it only appears on the rightmost part of the expression both times. So we can simplify this greatly. And then this turns out to be, so our map of f of x is map of f over x. So if we make it into this partial application map compose, it'll compose that with f. And so you apply it to f, you get map compose f. And then you apply it to x, you get map of f of x, parenthesized like this. Left map, it's, the 2 arguments, we can just swap them, do right map, and swap again. And then the outer product is this composition of left and right map. And so we can write this out with no definitions, and outer product is just flip dot map dot flip dot map dot, guys. I said outer product is good for making triangular matrices. Maybe you want a sort of richer kind of matrix that gives you upper, lower and identity all at once. So now, yeah, why am I doing functional programming when I'm just going to do the same things that I did before? The reason is because in functional programming we have functors. So yeah, does anybody here want me to explain what a functor is? Okay. Functors are functors, yeah. They're related to monoids, sort of. We can write the outer product with functors using fmap. And yeah, then we get something, I mean, it's the same thing, but now, actually, yeah, the conceptual improvement this gives us is that we can see very easily how it's keeping track of the nesting here. So in APL, you would make this observation by looking at the order in which the shapes are combined. Here, you can actually look at the orders in which the functors are nested. So, and these functors could even be arrays if you'll use one of the Haskell array packages. So you can see if you do an outer product with a list and a just, you get a list, or a list and a maybe, you get a list of maybes. So map over your list and just 3, and it'll map each element of the list with, and turn it into a just number there. Map over the list with nothing, turns into a list of nothings. We apply this to functions. What is this? So outer product applies a function to a functor and another functor, gives us a nested functor, and we apply it to arguments. Well, what it's doing here is to apply this function to this argument, and this function to this argument, and then pair them together. So on other slides, does anyone want me to explain this? How functions from A are functors? So yeah, we've got they are, and functor mapping is composition. Now, so let's look at what happens when we take the outer product on functions. So just going from the definition, I'm writing G and H, these first 2 arguments, because those are functions now. And here I've just rewritten the definition of outer product using composition. And now I'm going to apply this to 2 arguments. So outer product of f on G and H, giving me a twice nested function on x and y. So this thing applied to x and y. I'm going to expand the composition, which applies G to x. Then I'm going to do a substitution into the lambda here. So the usage of A is right here. This gives me f of g of x composed with h. Then I apply composition one final time, and I get that outer f on G and H. So the f outer product on G and H is the function that sends x and y to f of g of x and h of y. Now this is a pretty useful combinator, actually. This is something that in my own language, which is unhelpfully titled I actually implemented as split compose, having no idea that it's just an outer product, even though I was largely based on applying functors to array concepts. So yeah, this is something that I wanted independently. The idea that you'd do something to the left argument, do something to the right argument, and then combine them with a function. One nice usage of this in Haskell is to derive data.function on. So on is not quite the same. It applies one function to both arguments and then applies another function between those. But I can get on from outer by using the same function for both of those arguments. So I'm doing here, like if I say on FG, that's going to be outer F, the F outer product of G and G. So yeah, that should be pretty clear, right? That the substitution gives you a function that you want. Common use of on. We don't have this in APL, but we are probably going to add it in version 18. We'd like to add it as the over operator. And yeah, you can use it in exactly the same way. It's sort of related to a fork. Yeah, so a fork is what happened. A fork is in J if you write 3 functions, actually in dialog APL as well. If you write 3 functions right next to each other, it produces the function that applies both the left and right functions to both arguments, and then applies the middle function between them. So you can implement this using a fork by composing that left function with the left identity and the right function with the right identity. But it's kind of awkward, so I wanted a version that didn't have to do that. Should we take another very short break or asking more questions if you... Huh?
What would you want to do beyond compute? Where would we go?
So yeah, I have the next section is my favorite. It's about, it kind of starts with actually producing, well, not really the Cantor set, but iterations of the Cantor set in APL, and shows how APL really helps you think about that it just makes it much more intuitive, and it produces some interesting properties, and also some other problems which turn out to be related to that. And then after that, I have a section which is just some graphs on how fast the APL outer products are in dialog APL. Spoiler, sometimes faster than C. Yes?
I don't know if you did this already. Do you have a link to your slides?
I have not put my slides up yet. There.
Like you to?
Yes, I will. Yeah, they may, browser compatibility and stuff, so they may not look so good on your machine, but you can at least see everything.
And then the other thing I wanted to ask is what sort of industries or business areas is APL particularly popular with at the moment?
Where our money comes from is companies doing like finance, stuff like portfolio management. Yeah. We have users in just all sorts of like random fields. So yeah. So you can use it for all sorts of things. The people who pay us the most use it for shuffling money.
In a typical APL program, how big would the arrays be?
Very small, unfortunately. So you get the power of array. You get the performance by using huge arrays. But, well, okay, yeah. 2 things. You only need a very small number of huge arrays, right? Because you're just, those are your whole data, and you're working on those. So.
You're working on a data.
Oh, do you mean how big are like the biggest arrays that you can easily deal with? Close to all of memory. Like you could pretty easily work with stuff a third of the memory size. Yeah. And then you'll lose cache, like going over that array. Of course, not everything's going to stay in cache. So by the time you go back over, if you're going to do that, things have gone out of cache. So it'll operate at only memory speed instead of cache speed. But definitely still very fast.